Hi everyone. This is week 4, I think now. I think we have one more week next week. And then we are taking a break for Christmas, Hanukkah, whatever you celebrate or don't celebrate. All right. What is a chemical reaction in your own words? No right or wrong answers, well, except for the wrong answer. But we can pretend. Any ideas? Someone must know. Okay, so it's a chemical change. If we go back to grade 9, so Kelly says, when chemicals mix and create something new, pretty much bang on. One or more substances are destroyed. And one or more are created. Anyone got any examples of chemical reactions? So if I mix sodium chloride, sodium hydroxide plus hydrochloric acid, I end up with and James has just said the magical word, single displacement and double displacement. In a double displacement reaction, you start with 2 compounds, you end with 2 completely different compounds. In a single displacement reaction, we have A, I'm not going to use the exact example, but we would have A plus BC. We would end up with AC plus B. Any other kinds of chemical reactions you can think of? This one might ring a bell. A plus B to AB, which is our synthesis reaction. We have AB to A plus B. And that's called a decomposition reaction. So we have double displacement where we add 2 compounds together and we get 2 completely different compounds. We have a single displacement where we add a element to a compound. The more reactive A kicks B off and we get AC. A plus B creates AB is a synthesis reaction. So we're synthesizing a product from two simpler reactants. Decomposition, we take a product and we break it down into the reactants. So some terminology. Reactants over here. Reactants on the left. Products. This arrow stands for yields. So if I mix this and this, it yields these two products. A little bit of terminology for you. When we're looking at a chemical reaction, I'm going to work through this quickly. If you want to write notes, you're going to need to go back and watch the recording, which I'll put up after this. So in a chemical reaction, we have so here's my favorite reaction. Creating salt. So if we were using solid sodium, we would denote that with an S. Chlorine. This is going to start off basic, and it's going to ramp up really fast. Create solid sodium chloride. What would I put in the brackets if it was a liquid? I would just change it to an L. If it was a gas, I'd put it in as G. If it was NaCl dissolved in water, I would put it as aqueous. Okay. Quick quiz. How do we know when a chemical reaction is taking place? What are the signs? What's the evidence? Any ideas? So light, heat. Think about bread going moldy. What do you see? What do you smell? So we get color change. We get smells. We get formation of a gas. All of these are evidence that a chemical reaction has taken place. We can also have formation of a precipitate. We will be going through precipitate formation and the laws around that stuff, solubility, and predicting all the precipitates. Okay. When we're looking at chemical equations, we're given them in a number of forms. So we have word equations. So that would be solid sodium is mixed with solid chlorine to make 1 mole of solid sodium chloride. So Na plus Cl solid yields 1 mole of sodium chloride salt. This is what we call now the skeleton equation. So this is what we care about in chemistry. So I'm going to looking at balancing these two equations, because we have this pesky thing called the law of conservation of energy as well as mass. If I mix 1 plus 1, I can't get 3. Now people laugh, that's silly, but it's true. We have to balance the chemical equation. Everybody says, this is grade 9 stuff, why are we doing it? Well, do you know how many of my seniors this year did not know how to balance a chemical equation? Here's a hint, all of them. So they put in all this effort learning all these fancy complicated equations, and they still were getting the questions wrong. So we're going to practice balancing equations. Probably going to do a few. And I'm not going to start off easy, because that's too easy. So I'm going to give you a minute to tell me whether this equation is balanced or unbalanced, meaning it has the same number of atoms on both sides. So it's unbalanced. So we've got 5 carbons on this side. We've got 12 hydrogen and 2 O. On this side, we have 1 carbon, 3 O, and 2 H. Where do I start? Where was the most logical place to start? Am I going to try and touch this molecule? No. So I ain't going to touch this. How can I balance carbon? Could I add a 5 here? So that would give us 5 carbon. And 11 oxygen. So now the carbons are balanced. And in one foul swoop, we need to balance hydrogen and oxygen. Someone give me a number. So if I added a 6 here, that would give us 12 hydrogen and 16 oxygen. Now I've only got the oxygen left to balance. What number do I need? Okay, perfect. Now this is a skill you want to succeed in chemistry that you need to master and do quickly. So we're going to do 3 of these. Right, fairly simple one, got 45 seconds. Listen. Any ideas where how I can quickly balance that? Callie has it. I'm not going to try and balance changing this because zinc is already balanced. Pick the weak one at the back of the pack. Pick the small one, the easy one to take on first. But one more and then another 1 minute. This one, again, seems complex. It's quite so we take the easiest one is balance the sulfur first. So we change this to 8 SF6. Kelly has it there. Well done, Kelly. So we need an 8 on the end of SF6, on the beginning of SF6. So we would have 24F2, 8 SF6. Quick count, is that balanced now? So 48 fluorine, 8 sulfur on both sides. Okay, I'm not going to do any more of that. You guys can practice those in your own time if you like. So quickly go through, well, I'm going to write on the board, talk. So we've been quickly through all the types of chemical reactions. There is also combustion and neutralization. Combustion reaction occurs in the presence of oxygen. Elemental oxygen being O2, so methane creates and gives off heat. A neutralization reaction occurs between an acid and a base. So if we have sodium hydroxide, we add hydrochloric acid, we get water and a salt. What I want to focus on is this one. Okay. Remember, keep in your mind the combustion. In all I'm going to get that. Right then. So now we'll switch into enthalpy. I have distinct memories of trying to teach Hess's law last year. And being a very painful experience. Anybody know what I'm talking about here? We're talking about chain in or delta H. Yep, Kelly, you'll never forget the name Hess's once you've done it once. So we have two kinds. So when the energy is required to break bonds. It then energy is released when bonds are formed. Every chemical reaction is accompanied by a change. We have, hopefully someone knows this, exothermic, endothermic. Which one's which? What's an exothermic reaction? Releases heat or external. What about an endothermic? So endothermic result. So one way to think about this is an endothermic reaction. More energy was required to break the bonds than we got from reform. Exothermic reaction, less heat was required to break the bonds than we got from reform. And let's look at hydrocarbons. We looked at hydrocarbons last. So let's look at methane, propane, butane, and propane. Let's keep it simple. We burn methane in the presence of oxygen, which gives us this is an exothermic reaction. We know it's an exothermic reaction because it's releasing more heat than is being put in. Otherwise, we wouldn't use hydrocarbons as fuel. So for an exothermic reaction, the change in heat is a negative number. I'm going to make up some numbers here, so don't look them up later. Let's say, so break the bonds of CH or methane. We need 100 joules. So when we burn this side, we input 100 joules of energy. On this side, everything once it's burnt recombines, and let's say it releases 50 joules of energy when CO2 or H2O is created, and then another 50 joules when the bonds between carbon and oxygen form, they release heat. We would have a neutral number. So we have a neutral number, it would be 0. Not negative, nor positive. What if we had to input 150 joules, so if I needed 150 joules to break this up, and we only got 50 joules from these two, it would be a positive number, or plus 50. So on this side, this reaction would suck in 50 joules of heat from its because it needs another. Remember that pesky conservation of energy? This needs to balance. That's why it's endothermic. It pulls energy in from its surroundings in order to form the bonds. Now, this is obviously not the case with hydrocarbons. It's a negative. So we only put 50 joules in of heat to break up methanol. To reform this releases 50 joules of energy to the surrounding. Now this works with hydrocarbons because we use them for heating things up. Examples include burning coal, burning gas. We're getting more heat out of it than we're putting in. So if we put 50 joules of heat in, we should get 100 out, and 50 of that is released to the atmosphere for an exothermic reaction. Example of an endothermic is something like this instantly freezing ice cups. So we have, you basically crack it, all the chemicals mix, and in mixing, they pull in energy and they make the surroundings super cold and it instantly freezes. All right, we took a bit of time to get through this part. I'm going to. Okay, solubility. Let's set up. I'm quickly going to flush them on the screen. You can take a screenshot. Take 3 minutes. These are the basic solubilities. All these. So ammonium, all ammonium salts are soluble. All compounds of alkali group metals, of group 1 or group 1A, are soluble. Take a screenshot of that. Then we're going to look at this double displacement reaction scenario and predicting what is going to be produced, and out of that, what is going to be soluble. Right, 30 seconds looking at this. You can always use the link. In the shroud. Right, I'm going to close that. So we have ways of predicting the outcome of a chemical reaction. So this is a double displacement reaction, meaning that the two things that began are no longer there at the end. So I'm going to do this one. Sodium hydroxide. So I should be lazy and write aqueous. And magnesium chloride. So in a double displacement reaction, what happens is we end up with Na plus in solution, OH minus, what happens is, because they're all at different charges, they'll rearrange themselves. So they make sodium chloride and magnesium hydroxide. So if we look at our solubility rules, whereabouts is magnesium? So look at our solubility rules. Sodium chloride is always going to be dissolved aqueous. So the 1, 2, 3, the 7th rule down, 8th, all hydroxide OH salts are insoluble. So it's going to create a solid precipitate when I mix these two solutions together. So I mix two solutions together. Mix two solutions together. Because sodium hydroxide will break up into sodium and hydroxide. Magnesium chloride will break up into magnesium and chloride. They will then reform with this double displacement to form salt and magnesium hydroxide. Table salt is soluble. Rule number 7, verse number 8, says that all hydroxide salts are insoluble. So they will form a solid precipitate. I think we're talking one. So cobalt chloride in solution. Sodium sulfate. What are they going to break up into in the chart? What are they going to break up into? It's going to break up into cobalt. So, They'll do the same thing. They'll switch around. Again, making salt. Very creative examples here. No sodium chloride is going to be aqueous. What's our rule say about solvents? All solvates, except those of silver, lead, mercury, barium, strontium, and calcium. So in this reaction, no precipitate. So the key takeaway here is that when you mix two of these compounds, they will split up into the anion, the anion, and the cation, and then they will swap around. Use the solubility rules to tell you if a solid precipitate will be formed. Okay, we just got through about 5 weeks of chemistry. So I'll put this recording up, see you there, convert or Zoom, and I will see you guys next week for our last session for the year for this, and then we'll pick up again at another time.